Hello and welcome to Data Research Labs. For today's Advanced Excel Quick Trainer, we're going to discuss using z-scores in Excel. We recommend that for faster viewing, put your play speed on 2x and or jump to the chapters of interest in the timeline below. First up, what are z-scores? So what is a z-score? Well, before we get started, special thanks to wikimedia.org. They have a Creative Commons license for this normal distribution and scales chart. And I call out here that there's a normal bell-shaped curve. We're looking at the z-score here in blue. You'll see at the mean in the middle of the z-score, 0, and then we go backwards, -1, -2, -3, and we go forward, +1, +2, +3. That's our z-score, anchored off of the mean. So let's see what else we can learn about z-scores. It's based on the mean, red line in the middle, the z-score is. And the z-score is measured as the number of standard deviations from the mean. So in this case, the green line is saying +1 standard deviation. +1 standard deviation equals +1 z-score. Over here, if we go -2 standard deviations, that's the same as -2 for a z-score. And z-scores have some other interesting properties. They can tell you the probability or p-value. So in this example here, a z-score of ±1 standard deviation, from -1 standard deviation to +1 standard deviation, the area under that curve is 34 plus 34%, it's 68%. So the probability of a value landing within ±1 standard deviation is 68%. 68% of your values under the normal bell-shaped curve will be within ±1 standard deviation. And likewise, the z-score of ±2 standard deviations gets us 13.6 plus 34.1 plus 34.1 plus 13.6. The area under the curve to the red lines, -2, +2 standard deviations or z-score, same thing. The area under that curve is 95%. So you'll often see scientific experiments done within ±2 standard deviations. That means that 95% of the values will be within that realm. And then your hypothesis, if it's outside of that, then there's only a 5% chance that that's due to random noise. So that's why many scientific experiments are set at ±2 standard deviations. And ±3 standard deviations get you all the way to 99.7% of your values under the bell curve are within ±3 standard deviations. So often if you're looking for outliers, there'll be 3, 4, 5, 3 or more standard deviations out on either side. So here's an alternative view to what we just saw. Go ahead and feel free to copy and paste this if you want. It's Creative Commons license. I created this with Excel and Paint. But basically what this is going to show us is that under a normal bell-shaped curve, within -1 and +1 standard deviation, or the mean -1 standard deviation, we can find 68% of our values, and within 2 standard deviations we can find 95% of our values, and within 3 standard deviations we can find 99.7% of our values, leaving 0.15 and 0.15 on either end as outliers. That's why they're red. If you go right up the middle, the mean by definition, 50% of the values will be above the mean and 50% will be below the mean. So this is just another way to look at how the z-score is calculated and what it means and how it relates to standard deviations. So this -1, -2, it's standard deviations, or I could also just call it z-score. Next up, why use z-scores? So why use z-scores? Well, there's at least 4 reasons to use z-scores. One is for probability calculations. You can calculate the probability of a score occurring within a normal distribution. So in this example to the right, if you were wondering what the probability would be of an event occurring from the left all the way up to the mean, that's 50%. If you were wondering what the probability of an event was of something occurring all the way up to +1 standard deviation, or a z-score of 1, that's 84%. You have your 50% plus 34.1%, and so on. And you could go all the way out to all values up to 2 standard deviations. That would leave 0.1 and 2.1%. So you'd have 97.75% probability. The blue area under the curve is a probability of that event occurring if its z-score is 2, if the value is 2 standard deviations to the right of the mean. And we'll see examples of this later. A second reason to use z-scores is to compare two scores that are from different normal distributions. If you don't standardize your z-scores, you're comparing apples and oranges. You might have units in miles and you might have units in weights if for some reason you're comparing them. But if you standardize the z-scores, then your units are the number of standard deviations. So you can compare a lot of disparate measurements, if you will. And related to that is standardization for statistical models when you definitely have different independent variables. And like in the event of a linear regression model of house prices, and you may have number of bedrooms and you may have square footage. Well, number of bedrooms is small, 2, 3, 4, 5, 6. Number of square feet is in the thousands. Those are vastly different, and the weight on your criteria can get all messed up and out of whack. So by standardizing all of your different independent variables into a z-score, into the number of standard deviations to the left or right of the mean, model can be more accurate. And the fourth reason to use z-scores is to catch outliers, to identify outliers. Anything that exceeds plus or minus 3 standard deviations, where your z-score is in the red here. And that's basically, you can then say that, oh, that's a 0.3% chance that event is randomly occurring, or if it's a measurement, you can say that that's less than a 3% chance that that's just random white noise, that extreme outlier value is significant, etc. There's many reasons you want to find outliers. Sometimes you just want to throw the data away too when you're building a model if it's an outlier. Next up, how to calculate a z-score using the old school formulas. So how do you calculate a z-score using the old school method? Well, first a level set. What's the z-score formula? Well, the z-score formula is z equals x, you're given data value, each one individually, minus mu, which is the mean of the data, which is a fixed single value here, and then divided by, I think that's data, the standard deviation, which is also a fixed value. So that is the formula. Next, we lay out our data. So we have a bunch of data points there. And then we calculate the mean for that data, which is just the average of all of these cells. And that's fixed right there. And then we calculate the standard deviation for those same cells. Looks just like the average, except it's standard deviation .p for population. We're assuming that this is the population of all known values. If it's age, it's a group of people that's fixed, or whatever this data is, it's just made up data. That's the population, it's not a sample. And the final step is we calculate all these z-scores. And we use this formula here. C12 is our x value, so it's C12, and then the next formula, C13, C14, C15. As we copy paste the formula down, the C12 x value changes. But the G12 with dollar signs is absolute reference, and the H12 is absolute reference. Why? Because G12 is mu, is the mean of the data, is this value here. So as I copy the formula down, I don't want it to reference this blank cell and this blank cell. I want it to stay fixed on the mean, the single value for the set. So that's this equation literally looks like this for the different formulas I'm pasting it into down here. And that is how you calculate a z-score using the old school method. Next up, how to calculate a z-score using the standardized function. So how do you calculate a z-score using the standardized function? Well, first a level set. What does a standardized function look like? Over here in blue, you have z, your z-score, equals standardize the function name, open parenthesis, your x value, this guy or this guy or this one or this one, your mu, your mean, and then your theta, your standard deviation, 5.75 there. And the next step is to set up the data. We have the same data. Calculate your mean and standard deviation the same way that we did it with the old school method. And then it's different. The z-score calculation here in green is this right here, equals standardized. So I'm in cell E12, and I'm referencing cell C12, my x, and then I have comma, my mean, and comma, H12, my standard deviation. So you're not doing any math. You're not doing this minus this in parentheses divided by this like we were in the old school method. You're just laying out the same parameters, but comma delimited with a function call. So pretty similar, but a little bit different. Same arguments, different formula. Next up, example number 1 from education, student test scores. So for example number 1, the student test scores, we're going to do the demo now. So we're going to start by laying out a bunch of names and a bunch of test scores. I've done that ahead of time. And I've laid out what the raw test scores look like. I sorted in descending order the highest test score to the lowest test score, and there's what the line looks like. Now to do the z-score, we're going to do the old style. We're going to start with the mean. And so to do a mean, we're going to take the equals average, open parenthesis, highlight the whole range, close parenthesis, hit enter, and there's our mean. Now for the standard deviation, do the same thing. Equals std. We'll do population because our class, this is everyone in our class, so it's the standard deviation P. It's not a standard deviation S, which would be a sample. And there we go, we put that in, so 92.1% is the average grade, and 3.87, 3.9 is the standard deviation. Let's just make those look a little bit nicer. It doesn't really matter, but yeah, that's good. Okay, and now that we have the mean and the standard deviation set, I threw the equations over here so that we could see it. That is the same thing as what we have here. Well, used absolute references, but whatever, it doesn't matter. Oh, and I'm going to put this spreadsheet with all the examples on my GitHub website, and I'll put a link to that in the description below this YouTube video. So, last step after the mean and standard deviation is to calculate the z-score. We're going to use to standardize the new method. So equals standardize, double click, open parenthesis, we want our x value, comma, and then we want our mean, which is this one, and I'm going to hit F4 because if I don't hit F4, when I copy paste it, it'll change the row number and be wrong. So D22 and our standard deviation is D23. I'm going to hit F4 on that as well. Close parenthesis, and boom. 99 is plus 1.77 standard deviations. Pretty good. Paste it down there. So there we go. And what was the mean? 92.13. Right there, 92 is almost 0, the z-score, but it's 92.13, so it's a little bit less. 92.0 is a little bit less than 92.13, and that's why it's just slightly less than 0 standard deviations from the mean. Now it's interesting, just for fun, I was curious. When we have raw data, it's plotted like that. When we have z-score data, the slope's a little bit steeper, but it's pretty much the same line. You have it go down and it flattens out there. You have it go down, it flattens out there, flattens out again, drops down, flattens out again, flattens out. It's flattening out anytime 90, 88, 95, 93. That's where it's flattening out there. And then the z-score is the same thing. It would be what? 88 would be negative 1.06 right there. And finally, example number 2 from healthcare. COVID outcomes by compare group benchmarks. So this is example number 2, and we're going to use z-scores to compare my healthcare organization COVID-19 outcomes by compare group benchmarks. So way back in 1998 to 2004, I worked with benchmarks and compare groups and home healthcare and had a big national data set for the company that I worked for, and we did all kinds of slicing and dicing. And I thought it would be fun, roughly 20 years later, to make up some fictitious data around what a COVID-19 benchmark with length of stay in an ICU might look like. So I Googled COVID-19 length of stay, and they gave me a number, 21 days or something like that. And from there, I just generated a bunch of test data. So without further ado, we're going to go play around and look at what that might look like and how you might use z-score to do something meaningful with data and reports. So first we're going to peel back the problem description here and run through that. So you're given the following fictitious mean and standard deviations. They're calculated for a given measure, which is our length of stay in an ICU, from a CDC national database. It doesn't exist, but we're saying that it does. So you have this national database, all these healthcare providers, and you have this COVID data. And the calculations are broken out by compare group, where you have a national compare group that's the entire population. You have a region like the Northwest, you have states, Washington, Idaho, Oregon, etc. Let's peel back section number 2 here for the given benchmarks. And here's a fictitious measure ID, M0430, a fictitious measure name, average length of stay, COVID-19 ICU, a fictitious year, quarter, last year, a couple months ago, and then some compare groups that are made up, a national compare group, a region that's the Northwest, state that's Washington, medical service area, which is the Seattle region, and then a cohort group like large hospitals. So you have all these compare groups, and fictitiously we have the CDC national database, and we went through and took all the patients in the state of Washington and came up with a mean of 21.1 days and a standard deviation of 2.5 days for their length of stay average. And likewise, we're saying that we took all large hospitals across the nation for a cohort group and calculated the mean standard deviation. And for the medical service area of the Seattle region, which, unless you live here, it doesn't mean anything, but it'd be the Seattle, Bellevue metropolitan service area, where the prices are the same, because sometimes an MSA splits across, like the Portland, Vancouver, that's across 2 states, but they're one cohesive unit or regional area, and their prices are all the same. So anyway, all that stuff doesn't matter. What matters is that we're coming up with some compare groups, and we have all this data behind it, and whatever the measure is we're calculating, we're deriving a mean and a standard deviation for the given compare group. So the national has 1 million records. The regional Northwest would have fewer. It would have 200,000 records. The state would be smaller and have 100,000 records. The MSA would be even smaller and have 10,000 records. I'm making that up. But anyway, fewer and fewer records, your denominator's smaller, your count of potential patients. But with those smaller sets, you're still calculating a mean and a standard deviation. And we're doing this so that we can use z-scores to compare our score against the compare groups. So let's peel back section number 3, which is my data, my healthcare organization, HCO data. Same measure ID, same measure name, same year, quarter. All those are important. You need to be comparing apples to apples. But when I look at my healthcare organization data, and I have like 50 rows compared to the national, which is 100,000 rows or 1 million rows or whatever, there's my average length of stay, 17.9 days. But the national mean is 22.1 days. The whole purpose behind compare groups and looking at outcomes of you versus others is to determine, yeah, 17.9 is better than 22.1. But how much better? Is it statistically significant? Does it matter? Is it white noise? Is it meaningful that I have 17.9 days, which is fewer, which is great? A smaller, shorter length of stay in an ICU is a good thing. But how much better is it? So we'll peel back our 4th section here, toss it over to the side. And let's see. Oh, side note, all the compare groups sample sizes need to be 30 or greater patients, and then the z-score is valid. If it's less, then we might have to use a t-test, so just a note on that. But let's see how we laid out the data here. We have the same measure ID, whatever, make up something fictitious so you can store hundreds of them in a database. Then you have a measure name. You're going to want, for every measure ID, you have a measure name. That way they look good on a report, and you're tracking all kinds, it's like KPIs, you're tracking all kinds of different indicators. So measure ID, measure name, year, quarter, all the same. And then we have my healthcare organization score, repeating. This, interesting. It should be 17.75. They're supposed to match. I forgot to go up and change it when I was monkeying around with the data to make something work here. But anyway, 17.75 is my healthcare score. I repeat it. I put the compare group name, just copy paste it down. I copy paste the mean down. I copy paste the standard deviation down. All the white cells are just aligning the data from the two inputs above. And then I calculate a z-score. I have to use the standardized, and I'm taking my d value, comma, this mean, comma, the standard deviation. That gives me a z-score. So that tells me that my 17.75 is just less than 1 point something standard deviations below the 22. The standard deviation is 4. 22 minus 4 is roughly 16, so 2 minus 4 is roughly 18. I can't add. And 17.75 is just under 18, so I'm minus 1.06 standard deviations. And so we repeat that all the way down, and even though the means are all different, we can tell for a given compare group how many standard deviations is our score different from that compare group score. And it's nice because then we can take the z-score and make something meaningful out of it. We can calculate a p-value, probability. And so we want to know, is the difference, so in this guy here, 4.87, that's less than 5%. Our 17.75 score, the length of stay in days, 17.75 days, is better than the MSA for the Seattle region at 20.9. Now, 20.9 is pretty close to 17.75, closer than the rest of these. And yet, since the standard deviation is so small, this roughly 3 points of difference, 3 days of difference, is statistically significant, because there's less than a 5% probability that my 17.75 was better than the Seattle's 20.9 just due to random chance. My 3-day improvement is due to something that I'm doing in my hospital, healthcare organization. Policies, procedures, techniques, whatever. Something I'm doing means that my better score has less than a 5% probability that it's just random noise. It is a statistically significant difference, that 3 days. So anyway, pretty fun. I will take and put this entire spreadsheet out on my GitHub share, and in this YouTube video, in the description section, you have to expand it. I'll put a link to it so you can download it and play around with it if you like. But anyway, those are two very neat things that you can do with z-scores. And I hope you enjoyed it, and I hope you found that helpful. Thank you for watching, and please, if you found this video helpful, click like, or even better, click subscribe to increase this channel's reach.